Good morning, everyone. Good morning. I'm happy to see so many people after our last conference dinner. So it's my great pleasure to introduce to you Professor Karen de Clerck. She is a full professor and leads the Center for Textile Science and Engineering at Ghent University in Belgium. Karen is an expert in advanced fibrous materials with expertise to build on fibers, material characterization, production, and modifications toward many advanced applications. She has expertise around nanofibrous materials produced via, of course, electrospinning, with pioneering work on a range of applications such as color-changing nanofiber sensors, filtration, separation processes, composites, with many different toughening mechanisms. She is the author of more than 150 papers published in top quality, ranked in the 5% of the journals, and more than 150 conference contributions, with the publication Nature Materials, Nature Communication, Science Advances, Advanced Functional Materials in numerous covers highlighting her and her team work. So Karen, the floor is yours.
Thank you, Ulla, for the kind introduction, and thank you for inviting me here. And thank you all for coming over, and I'm sorry to have you wake you up all after the conference dinner. So indeed, as Ulla said, I'm based at Ghent University, and Ghent is a city in Belgium located centrally in Europe. And at Ghent University, I am heading, and Ghent is a lively city with a vibrant student life, but also a rich cultural heritage. And so if you haven't visited us yet, it's really worthwhile a visit. And it's at Ghent that I indeed lead the Center for Textile Science and Engineering. And within our center, we are focusing on textiles, so all type of fiber materials. Our core strategy there is to bring in innovation already from tackling the chemicals and the building blocks, the polymers, all the way through fiber production and processing towards different end applications. But for today, of course, I want to introduce you the core research group on electrospinning. And that's us in the lab. As you can see, not the electrospinning lab, but the chocolate making lab. Because indeed, we are Belgians, and for us, chocolates are very important. But I won't talk about our chocolate making skills today. I will introduce you to work on electrospinning, and for today I've structured my presentation on different material building blocks that we've been using over like the past decade, how we process them, in this case of course via electrospinning, and tune them for different properties and as a result different end applications. I've selected 3 ongoing research lines in which we invested a lot the last decade. And as a first, I want to present the electrospinning of polyoxazolines. And we've used that for biomedical and sensor applications. So what are polyoxazolines? This is the chemical structure of a polyoxazoline, and we are interested in them because they are biocompatible polymers with interesting stealth behavior. Moreover, as you can see, we have a side group here, and the side group can be altered, and we can just tune the properties from very hydrophobic to very hydrophilic polyoxazolines. Also, the thermal and mechanical properties can be tuned. In addition, depending on the side group, this allows for easy functionalization and for further broadening up the polyoxazoline platform. In addition, they're scalable and today already widely accessible. And moreover, we are very happy to collaborate on these polyoxazolines with our research partner, Professor Hogenboom at Ghent University, who's an expert in designing and synthesis polyoxazolines and gives us dedicated polymers that we then can spin. So the polyoxazolines as a polymer already have a wide range of applications, going from biomedical applications over sensors, food packaging, all the way to art preservation. But all these applications make it, of course, interesting to look at the electrospinability of these polyoxazolines. And we've indeed shown that polyoxazolines are easily spun from green solvent systems, such as aqueous solutions, just water and ethanol, into stable, large-scale membranes. And we've done that for a whole range of polyoxazolines, of course, depending on the side chain. For the more hydrophilic ones, we can use more water. For the more hydrophobic ones, we need to use pure ethanol. So we have demonstrated we can spin all of them, and that already allows us to tune the hydrophilicity, so we can use them for hydrophobic membranes, but also hydrophilic membranes. The hydrophobic ones are water insoluble, and the hydrophilic membranes are water soluble. However, for many applications, we would actually like to benefit to combine the high hydrophilicity of the more hydrophilic members of the polyoxazolines with the water stability. And therefore, we have introduced different strategies to cross-link these membranes and to bring in water stability, but still retaining the hydrophilicity. First strategy is a chemical cross-linking, and we've done quite some work on chemically cross-linking the PEtOx, as this is a very important member of the family, which is the most widely accessible and commercially available. For that, we've introduced a comonomer, which was functionalized with a cross-linkable group, and we've used silanol groups, benzophenone, and cinnamoyl groups here. Then we spun these copolymers from aqueous solutions again into nanofibrous membranes, and then we can cross-link them. The silanol groups already have an in situ cross-linking just through electrospinning, because they're cross-linked just in air. If you, however, want a good water stability, you also need a post-treatment to block the free silanol groups. For the benzophenone and the cinnamoyl functionalized polymers, we use UV light. For benzophenone, UVA, for cinnamoyl, UVB. The details on the cinnamoyl, because this is the latest member in the family that we introduced, were presented yesterday by the PhD student, Olmo Frateur, who did all the work on this. Then, when we've produced them and cross-linked them, we can then, of course, test their water stability, and indeed, we have increased the water stability significantly, making them suitable for also water-stable, but yet hydrophilic applications. The interesting part on the latest member, cinnamoyl here, is that by a UVC treatment, we can reverse the water solubility, the water stability, and we can make them water soluble, again, allowing for an easy removal after use if that could be interested for many applications. Also, the PEtOx polymer can be cross-linked chemically, but even through an easier strategy. We don't need a copolymer here. We can just co-electrospin it with succinic acid and then give it a thermal treatment, which will already induce our aimed water stability. We do not always need chemical cross-linking. We can also, for some applications, a physical cross-linking is good enough, and this is illustrated here for the PROPOX member. Most of these polyoxazolines are also thermoresponsive polymers, and so they have a cloud point, meaning they're water stable above the cloud point, but water soluble below. We take advantage of this water solubility to spin them from aqueous solutions, but then we can dip coat them, in this case with tannic acid, at temperatures above the cloud point and make them water stable over the full temperature range, both below and above the cloud point. And then the last strategy that we used to introduce water stability was using statistical copolymers and introducing here the ethyl oxazolene combined with a more hydrophobic oxazolene, and depending on the rate, and then we used both propyl and butyl oxazolines, and depending on, we could spin them from aqueous solutions again, and then depending on that ratio, we could either retain the water solubility or we could make them water stable without having to do another post-treatment. And in addition, of course, these statistical copolymers, depending on that ratio, that is ideal to tune the hydrophilicity. So now that we've made this polymer platform, so we've got a wide polymer platform available, we're ready to use it for different applications. And the first application I want to show you is biomedical applications. And for this application here in mind, we actually we took advantage of the very high solubility. So here we used non-cross-linked PEtOx. They are, because of the high surface area, they dissolve immediately if you bring them into water. And we wanted that because we wanted to use them as a drug solubilizer. Because today the most convenient method for drug administration is still oral drug delivery. But actually about half of all developed drugs with proven pharmaceutical activity suffer from a very low aqueous solubility, mainly because they form very thermodynamically stable crystal structures. And because of that, they can't be used, because although they've proven active pharmaceutical performance, they do not dissolve in our body and thus are discarded. However, if we could suppress this crystal formation, then all these drugs could become available again to combat many diseases. And the way to do that is to formulate them in an amorphous solid dispersion, so to keep the drug in the amorphous state. Today, this can already be done by traditional techniques such as hot melt extrusion and spray drying, but these are not sufficient for the very difficult to dissolve drugs. Then you can only have drug loadings of 10%, which is of course far too low. And that's where we came in and we introduced electrospinning, and our hypothesis was that electrospinning, since we have such a fast evaporation of the solvent, we can suppress the kinetics and we will be able to produce amorphous solid dispersions. So that's what we did. We did this for a range of model APIs which have all proven pharmaceutical efficiency, but suffer from a very low solubility. And as a polymer carrier, we used our polyoxazolene, PEtOx, because of its very high water solubility, also biocompatibility, and FDA approved as a food additive. In addition, it's important that the polymer carrier shows interactions with the drugs to stabilize the dispersion. So the first question is, can we spin them? And can we spin them to high drug loadings and form this amorphous solid dispersion? Well, as an, I can already say here, yes, we can, to very high drug loadings. And how do we do it? Well, we started off with the normal process conditions for PEtOx only. Then we tried to add the drug, but we could only add very small amounts, 10%. So we were not doing better than traditional techniques, so that didn't bring us anywhere. But that was due to the interactions, creating a high viscosity and giving it a difficult processability. Then the trick was to reduce the amount of polymer and to very low amounts, which are normally not electrospinnable, but because of the interactions, we could then, if we use a lot of drug, the rheology is sufficient again for spinning, and we could go up to drug loadings of 70–80%, depending on the API. And then this was also underpinned by theoretical studies such as Florey-Huggen theory of mixing, and that, if you do the theory, that predicts you that as long as you can keep it in the amorphous state during processing, you should be able to have a good mixing up to, depending on the drug, 60–80%. And we want a good mixing. If we don't have a full mixture, then demixing over time will lead to crystallization and a non-stable dispersion. So, is it indeed true? A theoretical prediction that we, of course, studied by experiment. And then we used XRD. Here, this is an XRD of a pure drug. So we see the crystalline peaks of the crystalline drug. If we only add a little bit of that crystalline drug, such just by physical mixture, to a PEtOx, then we see the amorphous big band with the crystalline peaks. So we can already pick up small amounts of crystalline drug in there. And then if we look at our Electrospun amorphous solid dispersions, we don't pick up any crystalline peaks, even at weight percentages of 70% of drug, so proving that we've indeed an amorphous solid dispersion and we don't have crystalloids in there. We also proved that there is a strong interactions. We've done this with infrared and DSC, and that these interactions are important to stabilize the drug. And then we experimentally confirmed we can indeed go to very high drug loadings for all the 4 drugs that we tested. But then, of course, we can make them? Do they now solubilize? Do they give a good solubility? We first tested this in vitro, and this is the solubility of the crystalline drug as being produced, which is, as you can see, very low. But if we use amorphous solid dispersions, we've increased solubility, depending on the type of API, up to a factor of 50 times. So, which was a really interesting result. Also, we've shown that this remains stable over time. You can store them up to a year. Here, data are shown for 25, but we can also store 50, 60, 8% for a year. Now, we've actually also stored them already for 3 years. It all works fine. We've also now proven the efficiency in vivo applications by monitoring the blood of dogs being administered with our nanofibrous amorphous solid dispersions. So for this application, we used the high solubility of the PEtOx. Then for the next application, I want to show you, for sensor applications, we wanted a low solubility, but yet a high hydrophilicity. These sensor applications, we've actually got a decade of experience in color-changing materials. We started off, because we are actually a textile group, so not only electrospinning, we started off with conventional textiles and traditional dyeing processes to make color-changing textiles. And that worked well, but there were some negative aspects. We had a lot of dye leaching and very slow response times. The slow response time was quickly seen could be improved by reducing the fiber diameter already for the traditional textiles. Then, of course, the next step is to go to nanofibers to increase the response time. We did different strategies, going from conventional dyeing of nanofibers, dye doping of the nanofiber solutions, all the way to dye modification of the polymers, which are then spun, also after post-spinning modifications with dyes through plasma treatments. They all work well. They give clear visual chromic materials, but if you want no dye leaching, then we need a covalent bond between dye and the polymer. We've developed this for a range of natural and synthetic polymers. So we've developed a whole platform of sensors there. But by doing so, it was also obvious that the type of polymer, if you use the same dye, the type of polymer will alter the halochromic behavior and thus the sensitivity. And this made it very difficult to design. We never knew where we were going to end up with our final sensor. what the pH range was. So we wanted to solve this, and this is where the polyoxazolines came in again and helped us out. So for this application, we used the water-stable polyoxazoline, we used the statistical copolymer, and then we used with a single dye, here alizarin yellow, by modifying the dye with different sized PEtOx groups, we could change the pKa value of that dye. And then we can combine both just electrospinning in water, and because also of the length of that PEtOx, we have no dye leaching anymore. We can keep the membranes amorphous or turn them into semicrystalline materials as we want, depending on the application. And then, if we've made those membranes, we can indeed see a very clear, very rapid visual response, for instance, for the detection of biogenic amines. And we can tune the response time from minutes to seconds, depending on the crystallinity of the polymer. Minutes has the advantage, it has a much longer, it also served for a much longer readout time, which could be important for some applications. Seconds give an immediate response, but a lower readout time. The sensors were reversible and stable. And as said, by tuning the length of this PEtOx chain, we could tune the pKa value and go for different applications, from detection of acids over monitoring wound healing, all the way to food spoilage detection. So by changing that length here, we could tune the pH change and detection limit. So these are two important applications that we used for our first platform of building blocks, polyoxazolines. So then let's move to a completely different building block system, the silica. And we use that because of the interesting properties, very high thermal stability of silica membranes and chemical resistance. So for completely different applications, where we focus more at resource recovery and catalysis. Our strategy in spinning silica is a bit different from many in literature. We did not use co-spinning with an organic polymer. This is often done. You need the organic polymer to make it spinnable. We wanted to spin silica only, so that we didn't have to remove the organic polymer. We could leave out the heat treatment, but that also allows us to bring in much more functional groups, which would be removed during such heat treatments. But that makes the building blocks more complex. So we have to start from the precursor building blocks shown here. The most common one is TIOS, shown here, and then through sol-gel synthesis, we have a range of hydrolysis and condensation steps, and we form a network, and then if we form the correct network, we can spin that network and then tune different properties. Of course, to be able to spin it, the sol-gel synthesis will determine the rheological behavior and thus the electrospinability. In our early work, we already showed that we do have an electrospinnable region, a range, but the range is very narrow and is moreover dependent on the type of precursor. So if you change from TIOS to another precursor, that range is different, and synthesis conditions dependent, making it a very difficult platform with a lot of trial and error. So we wanted to know more about the cross-linking kinetics, as more insight in the cross-linking kinetics would help us to understand the spinnability performance. And that's where the collaboration with Professor Doge came in. So we studied the cross-linking kinetics by quantifying the cross-linking. You can do it experimentally by NMR. That already gives you the fraction of cross-links of the silicon atoms. but it's quite tedious. It requires a lot of measurement parameters to be optimized. The measurements are quite long, and you only get an average value there. Then Professor Doge developed Monte Carlo modeling that allows us a more detailed information of the network structure, and moreover a predictive information if we use different building blocks. And this will be presented this afternoon by the PhD student Sophie Verschrage, also present here today. But I will already give you a sneak preview. So this is illustrating here that we've got a very good agreement of our model with our experimental data, and we can follow the QI species over time, both for isothermal synthesis and non-isothermal synthesis, which is needed for electrospinning. This will be explained in more detail by Sophie, but now that we've set up that network, that model, we now have access to the molecular structure, and we can tune it, we can understand it, why one is spinnable and another is not, and we can also tune the properties, because that model allows us to visualize and where the functional groups will be and can be used for further applications. So that brings us to the membrane properties, and for many of these applications we indeed need additional functional groups. Now, silica can be easily functionalized. They can be done by both, if you start from thios, and then you can first spin the membrane and then functionalize the membrane, or you can introduce different precursors, already introducing the functionalities during the synthesis. So you can, if you spin a thios membrane, then there are still some free etoxy and hydroxyl groups present, which can be used for further modification and bringing in, for instance, hydrophobic groups. Or you can immediately use a more hydrophobic precursor or a functionalized precursor during synthesis. And these can then be used for applications such as ion exchange membranes, solvent separation, and catalysis. So for ion exchange membranes, we developed them for both cation and anion exchange membranes for resource recovery. And the strategy was similar. We did a sol-gel synthesis of thios combined with another precursor, which was loaded with a functional group. We then spun them into membranes, and the functional groups are present, and these functional groups can then further be tuned, in this case, towards a conductivity for the cation exchange membranes for a high cation conductivity, for the anion, of course, for the high anion conductivity. And of course, the conductivity was increased depending on the ratio of functionalizable precursor. We also needed the membranes to be hydrophobic for these applications, so we functionalized them with a hydrophobic precursor. And then we can use them as ion exchange membranes. And we can use them for resource recovery of, for instance, wastewater. And what we want is we want to extract, for a cationic membrane, the cations from the wastewater to the cathode. This is now done by other ion exchange membranes, non-nanofibrous based, and that works well, but a problem with most of these membranes is that we have a strong fouling. So after use, there's precipitation on the membrane, increasing the energy that you need to operate the membrane, and so after some time you need to stop the process, you need to take out the membrane, clean it, give it a tedious cleaning treatment, load it in again, start everything all over again. Now, we showed that by using the nanofibrous membrane, just of the nanofibrous structure, they have a self-cleaning ability. You don't need to stop the process. They foul much less, and even when they foul, if you just switch off the power source it cleans itself, and you don't have to remove the membrane, and you can start up the process again. So that was a big advantage for these applications. Also, another thing which we want for ion exchange membranes is selectivity. And we illustrate this here for the anion developed anion exchange membranes for lactate recovery from bio-waste. So here we want the anion to go to the anode, but we only want the lactic acid to go to the anode. The other anions, we want to keep them in the fermentation solution. And again, we could show that for nanofibrous membranes, we have a much increased selectivity over commercial membranes. This was related to the type of functional groups we used here. Then in addition to ion exchange membranes, we also use these membranes for solvent separation. And here we took advantage of the tuning of hydrophilic, hydrophobic properties. When you produce these silica membranes, they're hydrophobic. But you can make them hydrophilic by giving them a heat treatment, or if you store them under humidity, in the end they will become hydrophilic. Won't go into much detail, it's because of network reformations and so on. Won't go into detail into that. But if you want them to remain hydrophobic, you can functionalize them with a hydrophobic precursor, and then you have a long-term hydrophobic performance. So we can make both long-term stable hydrophobic, but also long-term stable hydrophilic membranes. And it are then these membranes that we can use for separation of solvents. And why are silica interesting here? Because they're not dissolved by the solvents, and we can use them for less more harmful solvents, and we use them here to separate heterogeneous azeotrops such as toluene, water, but also methanol, hexane mixtures. And by just powering over, so we don't need any energy, it's a very energy low consuming process, we can have a high separation with a very high purity. And then the last applications of this silica are different catalysis processes in which we used the silica as an inert carrier for different catalytic nanoparticles. And again, the advantage of the silica is, for instance, the very high thermal stability, which is sometimes needed at very high temperatures for these catalysis processes. An illustration here is with titanium dioxide nanoparticles, which we used for degradation of herbicides. And we showed that it did not only decompose the herbicide into the first degradation component, but also the second and the third and so on components were nicely degraded, allowing for proving that we had indeed a degradation into a full unharmful product, because some of these side products are also harmful. Another example there is loading them with ruthenium functionalized MOF particles to do CO2 methanation, and then, for instance, by just loading them on the silica membranes, we have a much higher turnover frequency compared to the MOF particles alone on other carriers. So also these silica membranes, completely different building block with completely different end applications, but both as interesting. And then as a as a third research line, I would like to introduce you our work on using nanofibers in composite materials. And then when I'm talking about composite materials, I'm talking about fiber-reinforced composites. And these are the type materials we all know. They're all around us, and they're used because of their light weight and very high mechanical strength. And they're typically built up of textile fabrics, unidirectional or woven fabrics, stacked on top of each other and embedded in a matrix. The fibers are typically glass or carbon fibers, and the matrix is typically an epoxy. So they're very high-end materials, but they've got an important weak spot, and that is delamination. Because of the brittle nature of the epoxy, they're very sensitive to delamination, and once they delaminate, they give an immediate failure, which is to be avoided. And such delamination, there's two important types of delamination, an opening delamination and a shearing delamination. In reality, of course, both are happening in a true composite material, but in the lab we typically measure them both in mode 1 and mode 2 failure modes. So because of that, many strategies have been looked at to combat delamination, going from true thickness reinforcement by stitching the layers together, altering the matrix by adding both organic, inorganic nanoparticles, interleaving solid polymer sheets. All of these, some of them have indeed the wanted increase in delamination resistance, but they all come with many unwanted properties as well, such as through thickness stitching, of course, you damage the reinforcing fibers, which you absolutely don't want, because then you reduce the mechanical properties, so you lost the benefit of the material. And that's where we came up again with nanofiber materials as an interleave. It's a very easy technology. You just make the nanofibers, you interleave them in between the reinforcing layers, and then you can make a composite material out of it. So it can be introduced into the composite processing techniques which are used already today. And now I will show we indeed combine very high increases in delamination resistance, but with no damage of the reinforcement fibers, no substantial weight gain. We still have an easy resonant fusion and thus an overall improved mechanical performance. To understand this toughening behavior, I will guide you through a bottom-up approach and explain you some work which we did by toughening the matrix only to understand what happens there. Then looking at like a small fraction of a composite, just 2 layers of reinforcing fibers, 2 layers of carbon or glass fibers with the matrix in between. And then, of course, ultimately making a true size composite material, different stacked layers, and see if it also works in that material. We've done a lot of work on that. You can read that in our papers. We've done it for many different polymers, for a range of layups. We've used standard testing methodologies and developed some of our own. I won't go into detail to all of that, but just the basic principles here. So if we look at the matrix reinforced with nanofibers, then here in this graph, this illustrates you the energy needed to create a crack. And if you use a neat epoxy, then at a certain energy level, you will initiate a crack. But if you reach that energy level, then the crack will propagate immediately, and you will have immediate uncontrolled failure of your composite material. By introducing nanofibers in there, we have first of all increased the energy needed to create the crack, but also if we want to open up the crack further, we need more and more energy. And this is due to the energy absorption by yielding of the ductile nanofibers. And thus the nanofiber matrix. So we've illustrated that in the matrix, but now is this also present in a composite material? For that we looked at the bilayer here with the matrix in between, and indeed we tested these materials both mode 1, mode 2, and for both we have an increase in initiation of cracks and both propagation. And the reason is, if we look at the crack path, if we look at the cross-section of a tested sample, then the crack path crosses this interlayer a couple of times, and it's at these crosses that this nano-velcro effect becomes effective. So that works, but it's not as easy as it seems. There's many things that you need to take care of. The morphology of the nanofibers are important, the mechanical properties need to be optimized well, and you also need the proper adhesive interaction. For instance, we've shown that fine circular nanofibers are essential. If you have coarser fibers or ribbon-like fibers, you actually even have a negative effect. You even lower, this is the neat epoxy, and you even end up with lower toughness values. Also, the thickness, the web thickness, can be optimized to have as many crossings as possible, because it's these crossings that give the nano-velcro effect. We've shown that random mats perform best. That's quite good, because that's the easiest to produce. And you can use both direct spinning on the reinforcing fiber layers, or you can use them as standalone membranes to introduce in between. Mechanical properties need to be optimized. First of all, you need fibers with a high energy absorption during yielding. But if you do this at very high strain levels, then of course we have a very big crack, which is unwanted. So we need the optimal ductile nanofibers with maximum energy absorption at limited strain levels. Otherwise, you just open up the crack and they don't do anything. Also, the adhesive interaction is important, especially in mode 1. Because if you do not have sufficient adhesive, you will just pull out the nanofibers, and then they're not active anymore either. And for instance, PCL nanofibers give a very good adhesive interaction, but they dissolve in some of the epoxy resins. And then you lose the fibrous structure, and then they underperform in mode 2. Whereas polyamides perform very well in mode 2, but they don't have a good adhesive interaction, and they underperform in mode 1. And by using core shell, of course, we can take the best of both worlds, and we could optimize both mode 1 and mode 2. Now, core shell is a bit less easy to produce than just conventional electrospinning, and that's why we then, in our later work, moved to commercial PEBA block copolymers, which combined both the fiber retainment of the fiber morphology and the adhesive interaction all the way through the processing of the polymer. So now that we've developed that platform, are they really of use in true composite materials? Therefore, we produced composites as being as they would be used in industry, different layers stacked on top of each other, all with nanofibers in between them. First of all, the general mechanical properties, such as the modulus, was not decreased and was nicely retained. We didn't damage anything, and we didn't increase the weight substantially. But then, indeed, in fatigue, is suffering from delamination, and we could see that during fatigue we have an increased delamination resistance. So this is the virgin composite. So after a number of cycles, we will start to get a growth of a delamination, so crack, a small crack in the beginning, and then at multiple loading cycles. For instance, in airplanes, this is important. The wings, you have different small deformations there. You will start a crack to be formed. If we introduce nanofibers, we can delay that crack formation, and we can increase the number of cycles drastically. And for instance, for aerospace sector, a 5 millimeter delamination growth is a typical threshold before maintenance, and thus the nanofibers increase the time to maintenance significantly. Also, in impact testing, this is a movie on impact testing. This is slowed down, of course. This is a very rapid movement normally. We will have delamination. So on impact, the visual damage that you see is like this small impact, but in reality, the damage inside the material is much bigger, which can be visualized by, for instance, ultrasonic imaging. And then if we've tested this for a whole range of layups, unidirectional, different stacks, and then indeed nanofibers reduce the damage area for each of them. And that brings me to the end of my presentation, and I think it's just on time. By introducing these 3 research lines, and I just want to thank our collaborators, the research team, both the present and alumni members which were involved, and in specific Olmo and Sophie being present here and helping me with this presentation. The funding bodies and all of you for being here and listening to me.
Thank you so much, Karen. So discussion is now open. We have time for a few questions.
Karen, really nice presentation. I really like it. I have a question. A few years back, I was working with polyoxazolines, and I used benzophenone also for PVP, and we found a very high cytotoxicity of the material.
Yeah, so the benzophenone functionalized are not used for the biomedical applications. They are more used for industrial, we have more industrial applications in mind. And that's one of the reasons why we developed the cinnamoyl moieties.
Yeah, so that is, so cinnamoyl has better properties in this manner. Okay, thank you.
Thanks, Karen. It's really interesting. I was wondering, you use block-copolymer, one hydrophilic with oxazoline and one hydrophilic, and you managed to make between 60 and 80% of non-soluble drugs. I think, correct me if I'm wrong, that depends on the loading, depending on the block, which is non-polar, right?
But for the drugs, we used the PEtOx. We didn't use the copolymer. For the drugs, we used a homopolymer, PEtOx, the very hydrophilic one.
And it managed between 60 and 80% loading effect?
Yes.
Okay.
Yeah.
Okay.
Thank you for your very interesting presentation. It was very clear as well. I was wondering about the UV cross-linking, the amount, maybe I not caught it, but the amount of group in the copolymer that was able to cross-link, and also maybe if you have this information, the cross-linking time under the UV.
Yeah, it depends on the type of cross-linker. I don't know by heart for each of them. I know for the cinnamoyl, because that's the latest member, and you can discuss with Olmo. We've tried 5% and 10% modification. Of course, not all of the groups are cross-linked, and that's part of Olmo's work. The modification, the time of cross-linking, we've now done a cross-linking after electrospinning, and we needed quite long times because we used a very low intensity UV lamp. Our future work is using a much higher intensity UV lamp and doing in situ cross-linking. This is what Olmo's doing now.
Okay, thank you so much. Let's thank Karen again.